Welcome to this webinar. I'm Ruth Slavid. I'm chairing this today. I'm delighted to be chairing on this subject because I think we all know it's such an important one. On the one hand, we know the great advantages of designing and building with timber. On the other, we are increasingly aware of the need to prevent fire, and regulations and insurers' concerns are both keying into that. So I think it's important that we discuss this, particularly because we are going to be hearing both the concerns and some of the proposed solutions, the ingenuity and imagination of designers and manufacturers. So just to tell you a little bit about how today will work, we will be hearing from 4 really interesting speakers who I will introduce to you in a moment. They, I'm sure, will raise lots of questions in your mind, and do please send those questions in as you think of them. There's a question button, and then we will select the most relevant and pertinent questions at the end when we'll have a group discussion. So just to let you know who is going to be speaking today, and I think we're going to hear our speakers. We will be hearing from Dr. Jim Glockling, who is Technical Director of the Fire Protection Association. We will be hearing from Anna Beckett, who is an associate with Webb Yates Engineers. We will also be hearing from David Murray, who is Head of Technical Affairs at MEDITE SMARTPLY. But first of all, and I will be hearing him present to us in a second, we have Steve Wallis, who is Senior Associate at dRMM. So, Steve.
Yes, thank you. I'm here representing dRMM Architects, who are the architects of the Charlton workstack that I'll be describing. We're a practice of approximately 40 talented architects and designers who are quite multinational in our origins, and are currently represented by 65% female to male ratio, which is something that we're very proud of. So as I said, I'll give a brief background to the Charlton area to inform the discussion about the project. The Charlton area is located to the south of the River Thames and just east of Greenwich. It's an area that's historically been of industrious uses, and the proximity to the docks really led to a ribbon of development along the south of the Thames that was a key part in the delivery of goods in and out of London, but established as an industrious zone south of the Thames. And throughout the Industrial Revolution from the 18th century, this area infilled with various industrial uses, supplying manufacturing, delivery, wholesaling, and warehousing facilities that served the docks and that area. And these various uses continue to this day. This is a map by We Made That in their study of the heritage, of the Charlton Riverside Employment Heritage Study. And it shows the various mixed uses that exist today, ranging through manufacturing, wholesale warehousing, commercial type retail, and other such uses. The Charlton Riverside area, like all areas of London, is under immense pressure to transform and move with the times. And this is an extract of the Charlton Riverside SPD that imagines a mixed-use development coming forward for the area, and certainly changing drastically from the industrious heritage. So we were approached by the Greenwich Enterprise Board, who are a small organisation that act as landlords, providing industrious tenancy or premises for light industrial, small, medium-sized businesses. And their ethos is really about providing very good quality workplace that's suitable for making, creating, manufacturing, distributing, but to do so at an affordable rate, and provide letting arrangements that are flexible and allow businesses to move, expand, contract, and really foster growing enterprise. They've got several properties that they've developed in and around the Greenwich area, and they found the site and approached dRMM. So the site itself is located on the south of the Charlton Riverside industrial area. It's located on Woolwich Road. So you can see the Thames Barrier Park there, and the Charlton Football Stadium to the bottom of the screen. The site's really nestled right on that southern periphery of the industrial area, and our immediate neighbours are Selco, building merchants, with an industrial park to the east there that provides large-scale retail. But to the south of Woolwich Road, it's defined very residential, and it's that periphery that's very interesting for the site, that periphery condition. So our approach for the site was really in review of the site conditions, and we established that this periphery condition that the site has on the industrial park gave us the opportunity of creating a billboard feature for the site that is in part signposting the industrial uses for the area, but also needs to be of architectural merit to create a pleasant visual connection or approach from Woolwich Road, of which there are two key viewing axes of the building, from the roundabout on the right hand side of the image and Woolwich Road to the left. We were aware that once you get above the first or second floor, amazing view corridors open up around the site, and these are shown in the blue arrows towards the barrier, Greenwich Peninsula, even towards the stadium you mentioned. And then the other key consideration for us is the solar diagram, which is shown in yellow. So the site benefits from really great daytime solar sun aspect as the sun moves around the south. But we're very aware also that could lead to quite intense sun or solar gains from the west and setting sun. And in terms of the site, it's pretty much what you would expect from this part of London. Very large industrial sheds for retail and industrial uses, and the site itself quite overgrown and unkempt. So our brief from GEB was to create approximately 14 workshop units that would be around 100 square metres in size, ideally standardised proportions. And we went off and had a little look at this. The diagram on the left is really the traditional approach to a light industrial workplace and that typology, which is a single-storey or predominantly single-storey shed arranged around a parking and servicing yard, and this is, as you can see, quite space-hungry. With our tight site, getting 14 units on the site would really require stacking these vertically. And so we came up with a diagram whereby we would have servicing provisions, loading and like on the ground floor, and then a series of units that are stacked vertically on the site and accessed through lift and stair placed at the back. Vastly reducing the site area that's required to create these units, and you can see approximately 1,800 square metres on the left for the low-rise sheds, and just shy of 600 square metres building footprint for our version. So very efficient way of creating the floor area needed. Architecturally, we wanted to create a building that was quite well suited for the use, but as I said, the site operates as a bit of a billboard for the area, and so we thought that a visually arresting building was appropriate. And this diagram explains that process of design, the stacked arrangement of the units, which we then carved away a profiled or progressive cantilever to the west side, which allowed various lengths of unit to be created within the building, which would allow the units to appease different types of users, but also ideally allow users to move throughout the building as their operations expanded or contracted. The cantilever also assists the solar shading to the west, providing more shading to that aspect and hopefully reducing the solar gain in the afternoons, and creates this visually arresting profile. So the image on the right being the final building. And as a practice, we have a keen interest in timber buildings, and this was really an opportunity to explore that typology and construction method in further detail. So we really like this analogy of the work stack, log stack arrangement, whereby the building is created of timber, and the lengths of timber are effectively changed to suit this progressive cantilevering form that expands on the west side. So to talk about the arrangement of the building, as I said, the ground floor works quite hard in providing the main entrance and the basis of the vertical circulation through the building. There's a central loading bay that is sized to allow a goods vehicle to come and reverse in, have direct access to the lobby and goods lift. There's then stair in the top right hand side of the diagram, allowing movement through the building, and otherwise a bin store completes the communal services of the building, with 2 individual units on the ground floor. There's then 3 units on each floor as you move up the building, and these are arranged as shown in the plan, really. So all accessed from that main circulation lift. And then as you move up the building, those progressive cantilever means that the size of the units expands up the building, creating units up to 115 square meters at the top. Lost a page. There we go. And so this is the view of the building in a rendered image. So you can see the cantilevered form to the west. The design of the exterior of the building is really to take reference from the industrial area of the site, and we're deliberately using quite robust and common building materials that you would find in an industrial area. There's polycarbonate cladding, which you can see on this main elevation, and corrugated steel cladding to the 3 sides that you can't see here. So very similar materiality that you would find in industrial parks generally, quite hard-wearing. So to talk about the timber construction, we worked very closely with Arup as the structural engineers to create the structural arrangement for the building. The principle is the building's quite well sized to take advantage, I suppose, of the maximum cross-laminated timber panel lengths that are available. And the central diagram shows the intent of using really long panels that span the width of the building and tie everything together as floor panels. And the wall panels, conversely, quite long panels that span the length of the building and allow that structural cantilever to progressively increase over the width of the building. The use of cross-laminated timber also meant that we could leave that finish exposed within the units themselves and generally to the interiors. So the walls and soffit of the units will simply feature the cross-laminated timber, the structural finish of the building, which will be left exposed with, as you can see from the images, quite impressive daylight and views that are accessible from that western aspect. I suppose one thing to say is probably on the structure as well is so all of the cross-laminated timber is left exposed in the interior of the building, and the the arrangement with fire control within the building is that the timber allows, or the width of timber that's been allowed, allows for a charring zone within the one side of the timber. So if there is a fire, the timber outer surface will char and become impervious to further deformation of the overall panel. So it's a very efficient way, an elegant way of controlling fire within the building. And then finally, I'll wrap up with some photographs of the building that's currently on site. So we're working with Parkinson contractors who have been on site for a little over a year now, and the CLT structure has been completed, topped out. And you can see the formation of the building form here, the scaffolding to one of the sides, and the progressive cantilever very clearly shown there as the building rises. The view looking up towards the progressive cantilevers on the west side, with some temporary propping in place currently that will be removed later on. And a view of the interiors before the fit-out works, where you can see the simplicity of the building form, perhaps, and the very clear desire of these workplace units that won't really be finished too much further beyond some mechanical electrical fittings and a nice rubber flooring. That's a quick roundup of our work stack project, which is due to completion this summer. Happy to take your comments or questions.
Well, we have had some questions, and do send more in because we'll be able to discuss them at the end. I thought that was really interesting, particularly the way that the architectural form both worked, as he said, as a billboard, but actually gives that flexibility in the size of units that people can occupy. So we've had a great start, and I'm now moving on to our next speaker, who is David Murray, Head of Technical Affairs at MEDITE SMARTPLY. David.
Between the UK and Ireland, the government target is to build 330,000 new homes every year for the next number of years. And it's great that a high proportion of these buildings will be built using timber frame construction. And it's important that this is not just done for environmental reasons, but it's important that it's done safely at all stages of construction and in the occupants of the buildings. So my presentation this morning will focus on one aspect of safety of timber frame buildings, and that is the use of flame retardant OSB to enhance the fire safety of timber frame during construction. So fire is a huge topic and a very complex one as well. So the scope of the presentation this morning will be on standard panelized timber frame construction. So that's platform timber frame, low to medium rise buildings, less than 18 meters. So we're looking at 6 stories and below. And the focus of the presentation will be on mitigating fire risk during construction, either intentionally from arson or accidentally from hot works on site. Out of scope will be massive timber construction, CLT, high-rise buildings, and the fire resistance of building systems, cladding systems, and completed buildings. That's for a different day. So getting straight into it, if we look at the benefits of flame retardant treatment, if we look at the 4 stages in a fire, there are ignition, fire growth, the fire fully develops, and the fire decays. And fire needs 3 components to start and keep going. That is a heat source, a fuel source, and oxygen. So if we look at a temperature versus time graph of, first of all, an untreated wood product, you have the ignition phase, and then you have a very rapid fire growth until flashover is reached, which is when all of the hot gases ignite and you have a very fully developed hot fire reaching and over 1,000 degrees Celsius in a room in a very short space of time. As the fire continues to grow, it continues to consume the fire load, so the furniture and everything that's in the room, and it eventually continues to eat away at that fire load. And eventually when the fire load is gone, it decays over time. So the important part here is that from ignition, the fire growth stages are very rapid. The temperature rise is quite severe. On the other hand, if you look at an FR treated wood panel, you have the same scenario here. You have the same shape of the graph, but the difference here is the reaction to fire properties have now been enhanced. So reaction to fire covers things like the ignition, the spread of flame across the surface of the board, and the heat release, as well as smoke and droplet formation as well. But if you look at those reaction to fire properties, they significantly enhance and slow down the growth phase of the fire. So what we're trying to do is we're trying to prevent a small fire from developing into a fully developed fire. So you can see here the progression towards a fully developed fire is much slower at a lower temperature. Flashover temperature will be in the same region here. It just takes longer to get there. The same thing happens once flashover happens. The fire engulfs the room, it really consumes all of the wood, all of the materials in the room, and eventually it dies out in the same way. So the key to performance here is the enhanced reaction to fire properties of the treated wood, which slow down the growth phase of the fire, again, preventing that fire from becoming, the small fire from becoming a big one. And this gives occupants time to escape the building, or site workers time to escape if it's during construction. And the key here is that small fires will be extinguished more quickly and prevent damage, and are far more effective than obviously firefighting a fully developed fire. So moving on then to look at the benefits of inline FR addition. What I mean by that is where we add the flame retardant during the OSB manufacture. So you can see here two OSB samples, one FR treated and one untreated. And on the right-hand side here, you see the same samples just from the reverse. You can see we have a thermal imaging camera here at the back. So this way the samples are reversed. You're looking at the untreated one here on the left and the treated one here on the right. So immediately you can see untreated OSB catches fire and ignites very, very quickly after ignition, whereas the treated sample continues to char. You can see it is still a very hot surface on the board, but it's not, crucially, it's not igniting, and the charring is protecting the timber beneath. So this is the benefit of a wood panel that's treated during manufacture. You have that FR treatment the whole way through the panel, so you have that continuous protection. So the ignition is delayed or even prevented. And the benefit of this is obviously when the panels are used in a factory or on site, the edges are protected, so it's no issue when you cut the panels on site. So here you can see after 3.5 minutes, the untreated sample has burnt through. You can see the smoke here at the background after a very short time frame. And on the heat sensor camera here, you can see on the back significant heat, obviously, as the fire has burnt through. And on the treated sample here, you can see that the charring rate is actually helping to insulate the panel as well. So this is an additional benefit of a flame retardant treatment. So it prevents, it keeps that temperature lower, so it can prevent other combustible materials from igniting in the background. Also, there's very little smoke produced here. The key to this slide is that the product is CE marked for both structural and fire performance, and that is really, really critical. And what that means is that we manufacture the OSB and it is CE marked ex-works or from the factory. We can stand over all of the structural properties of that panel, as well as the fire properties, whether it's Euro Class B or FR build or whatever. This is purely for illustrative purposes only. It's not a BS or an EN test. This was part of our R&D as we were developing the product. We'll look at more formal testing a little bit later on. So if we look at, go back, I suppose, a decade or so ago, and you can see where the problem, I suppose, the issue started with timber frame during construction. There were a number of high-profile fires on timber frame sites during construction, which is obviously a serious threat. If a building like this does go on fire and it's adjacent to an existing row of buildings, the separation distance here is critical. And if a burning building poses a threat of fire on the existing buildings, that's obviously a very significant risk and threat, and one that needed to be resolved. The benefit, or the good thing about this story, is that the timber frame industry as a whole responded extremely positively and very quickly to this growing challenge and problem, and produced a set of design guide to separating distances during construction. And this is a very detailed, technical, comprehensive set of guidance documents, including product papers and technical papers, which are endorsed by CIREG, the Construction Insurance Risk Engineers Group, and the HSE. And what this is aimed to do is to reduce the risk of this happening. And if a timber frame building does catch fire, that it won't set fire to adjacent property. So we're going to look at that in a little bit more detail next. So first of all, the first test that we had to do as part of this STA testing was called the corner ignition test. And this measures flame spread and burn through. And as you can see, it's slightly different to the SBI test for Euroclass in that the stick formation here resembles an arson attack. It is offcuts of timber and sawdust and paper that would be found on a typical building site, helped along with an accelerant like petrol or whatever. And immediately you can see here that the OSB is doing its job. It's starting to char. And this is due to a chemical reaction between the FR chemical and the OSB. So immediately you have a very intense fire that is suppressed by the FR OSB. And that's the key to success in the product. The char layer continues to grow, and you can see that the additional fuel source to the fire is cut off. Now, what this does after a few minutes is you can see, even though the fire is fading, you can see that the height is dropping down. Just about now, you can see a secondary fire is growing and developing just about now. And you can see that second burst of flames as the wood sticks fall into the fire and the fire continues to consume the fire load. Why this is important to measure this, you think the fire is gone at this stage, but really if you look in the corner of the OSB there, it's a very, very hot, intense ball of fire in that corner. And if that is continued to, if that continues to grow, if the board isn't treated behind it, then it will penetrate the board and it can develop into a fully into a full-size fire. So crucially, the OSB held back the fire and didn't allow it to grow. And obviously, in a real-life situation, that would prevent the fire from spreading into across the building. And after 30 minutes, then the fire eventually dies out. It's a 40-minute test. What this doesn't indicate is 30 minutes fire resistance. That is a completely different thing. We covered that in a separate AT webinar last year, but there are similarities. But the important thing here is that, again, the flame spread and the burn through are restricted by the flame retardant OSB. The next test, from passing the ignition test, the next test we had to pass is called the small room test. And this measures heat flux, flame spread, and burn through. And this is a very severe test. And as you can see, it is a compartment, a timber frame compartment built up in various materials, non-combustible insulation, flame retardant OSB on the sheathing and on the floor deck. And if you pass the ignition test and this room test, then you achieve FR build certification for your products, which is what we did. So here we have the fire after about 6 minutes 40, so approaching 7 minutes. This is when the heat flux at the highest point in the fire at flashover is achieved after about 7 minutes, and it reached about 3.7 kilowatts per square meter. So a very hot, very intense fire engulfing that room. And you can see obviously that the OSB, the FR OSB here in the floor is now being attacked by the full rigors of this fully developed fire at flashover. And also the flames are attacking the FR sheathing here on the outside. So the aim of this test is to prevent burn through of the floor and also no ignition in the sheathing. So how does this look in practice then? We look at a worked example of separating distance using the STA separating distance guidance. If we were to look at an example of a new building, a new timber frame building being built beside an existing row of houses or a building here, you want to know what the separating distance is here between the two buildings. Again, assuming a 4-story building and a 19-meter length, here it is in section and here it is in plan. So we want to work out the distance between these two buildings and what can be done safely. First of all, looking at untreated, category A. This is a table taken from the guidance, and it looks at the number of timber frame stories and the emitter length. So that, looking back at the diagram we just saw, if we go down to 4 stories and across to 19 meters, you can see that the separating distance is 21.25 meters. Next, looking at category B3, which is FR treated. And this is where SmartPly's wall and floor system will fit in. Again, you come down to the number of stories, 4 stories and across to 19 meters, and you can see the separating distance has been reduced to 12.25. So effectively here, you've reduced the separating distance by 9 meters. by using flame retardant materials in the build. And that's a significant amount of value in terms of real estate in built up areas, towns and cities and so on. So that's the theory of it. In such a short presentation time, there's obviously a lot of data and certification in the background of these products, but just looking at some of the recent projects that we've completed on site, the picture on the left here is the product FR build in a flooring application in an affordable homes development in East Sussex by Gibbs Timber Frame. The middle photograph is again a flooring application. This was a 7-story building in Liverpool for student accommodation. I believe it was 6 stories on top of the masonry ground floor, and it was obviously a combination. You can see a combination of timber frame and masonry there in the background as well. So a good example of the flame retardant board being used in medium rise construction. The photograph on the right then is slightly different. This is an 18mm FR panel used as wall sheathing. This was designed by the structural and fire engineers from first principles. And the reason 18mm FROSB Euroclass B was chosen for this was to, first of all, to give enhanced fire safety in the cavity. But secondly, it was to give increased fixability of these helping hand brackets, which are fixed into the sheathing. And these are obviously to fix the rain screen cladding onto the brackets. So the problem with using non-combustible boards, or some non-combustible boards, is they're quite brittle, so they can break when fixings are attached into the side of the wall, whereas the OSB provided a very solid grounds for fixing these helping hand brackets. So that's another great example of, you know, medium rise building, how FR products can solve the challenges relating to fires in medium rise buildings. So there's lots more available on our website. If you have a look at our website in the case studies section, you'll find lots more examples of FR build and also Euroclass B applications for the product as well. You're very welcome to have a look at the website. And again, thank you for your time this morning.
It was fascinating to see just how rigorous those fire tests were, and also how pleased developers will be when you can cut down separation distances. We're getting some great questions in to fuel our discussion at the end. Please do keep sending those questions. I'm sure that there will be more things triggered by our next speaker, who is Anna Beckett of Webb Yates Engineers. Anna.
So I work for Webb Yates Engineers, and we are structural and building services engineers. And we have a very big low carbon focus. So we do a lot of work with timber, but we also work with lots of other low carbon materials as well, and try to put sustainability right at the top of the agenda for our projects. So I have some of our projects in timber here, which I am going to talk about as we go through, but also Clark and Mile Close at the bottom, which is a load-bearing stone structure, which is really great as a low carbon option. And also just under our logo is a rammed earth project that we are doing at Salisbury, which again, really low carbon material. It's something that we're looking into across a really wide range of our projects. So talking about timber and using timber as a structural material, timber gets a bit of a bad rep, which goes back quite a long way. So in London, following the Great Fire of London, timber framing in buildings was completely banned. And the London Building Act of 1667 dictated that new buildings had to be constructed in masonry. And so going forward from then, there's quite a long period where we didn't build in timber very much. And as sustainability has come back, or not back, but become a much bigger issue, we've started to build in timber much more. And that was sort of really gaining some momentum, and has been interrupted by the sort of Grenfell fire and the Hackett review following that. And again, building in timber has become much more difficult, and it's again has a perception that timber is going to ban and be this really big issue in buildings. A lot of the other materials that we design with, so steel, concrete and masonry, all have a level of inherent fire resistance, whereas timber itself obviously does burn. And while actually when you put it into a building that it doesn't burn in the way that you would expect it to, that perception seems to be influencing a lot of the way that it's used at the moment. So I'm going to talk about some of our projects, but the ones that are constructed, because a lot of the changes that are happening with regards to regulations and things are very recent, we don't have very many completed projects where those sort of changes have been implemented. So I'm going to talk about some of our projects where we haven't necessarily done the things that I'm talking about, but where you can see how those changes would be used. So this is York House, which we did with DMFK for the office group. So this is an office refurbishment project with a front extension and a roof extension. The front extension was done in CLT and glulam, and the roof extension is all in CLT. And in this situation, the CLT worked really well, especially on the roof, because it's really lightweight. And so when you're adding an extra story onto an existing building, structurally that has a massive advantage. And it also is a site that's really constrained. So running along the sort of top of this plan is Pentonville Road. There's very little space for loading and unloading. And so actually building in CLT was really good because we could lift the CLT straight off lorries on the road, store it on the roof because it was really lightweight, and really limit the amount of space that was needed during construction. And as we all know, the embodied carbon for timber is actually really low, and you also get sequestered carbon in the timber. So here, when you take into account all of the carbon for the building, the overall rate was 375 kilograms of carbon equivalent per meter squared, which is well below the REBA and LETI targets for building, and that's without subtracting the sequestered carbon that you get from the timber. So in terms of fire, this front extension would be the part that would be the biggest issue. During the work that we did, we looked at the CLT and the thickness of the CLT, taking into account charring, which I'll talk about a little bit more as we carry on. And the glulam is also sized to allow for charring, but because of the point at which it was built, there wasn't really any issues with that, and we were able to leave it all exposed exactly as it is here. At the roof level, again, we were able to leave all of this exposed, and we just had to apply a coating which would prevent the spread of flame through the building. If you were building this now, so this building was completed at the end of 2019. If you were building this now, I think that you would have to do a lot more, particularly where there is a joint between the CLT wall and ceiling, or the wall and the floor, because the joints are a really big issue in these CLT structures, and sort of preventing the buildup of heat in those joints is a particularly big issue. I also actually think you probably wouldn't do this in CLT now, because there are lots of issues with CLT, sourcing CLT and the cost of CLT following Brexit. So you would probably be more likely to do it in mass timber if you're going to try and do that. But the way that you would treat it for the fire would be significantly different. One project where we have started to deal with that is this project that we are looking at on Old Street, which we have worked on with Mary Duggan Architects, which is a new commercial building with retail space at ground floor and then workspace on the upper levels, which is due to be completed at the end of this year. So as you can see in the image here, the design has these pairs of steel T's within a CLT box. So the CLT is forming both the walls and the floors. And this meant that we could maximize off-site construction. So we could construct these as a box, which could then just be stacked on site and delivered straight from the back of a lorry. Again, similarly to the previous project that I talked about, to limit the amount of space that was required on site for construction. On this project, it was, because it was all CLT, it was really important that we had a fire engineer who was familiar with working with timber structures and had some experience with timber buildings, but we also found that it was really important to use building control who also had experience with timber buildings and were familiar with this type of construction to be able to get everything approved. This, again, as I was kind of starting to say on York House, this project again has got CLT walls and CLT floors, and here we were given the advice that either the ceiling or the walls needed to be covered to achieve the fire resistance because of the buildup of heat in the joints. And by protecting one surface, you could limit that in the joints. We also found that where previously we might have been able to just specify the charring depths in the timber, we actually had to do a full-scale test to prove that the CLT was going to respond in the way that we were expecting. So it's definitely a move towards much more of a physical testing rather than to sort of support the calculations that we would have previously done for timber in this kind of situation. And going forward, we kind of expect that that will eventually be replaced by kind of really good fire modeling, which will be able to replicate that. But at the moment, it seems to be that full-scale testing is being required for approval for structures like this. So as I mentioned earlier, if you design with steel or with concrete, the way that you would look at them in a fire situation is very different. For concrete, you just need to make sure that it's got enough cover to the steel so that you don't have an issue with fire. With steel, you would apply a coating to it to prevent it from heating up. With timber, if you're going to leave it, you have two options. Either you cover it, or if you're going to leave it exposed, then you look at the charring depth. So the picture on the top left is just standard softwood, and we have pretty good sort of methods for calculating the charring depth, which are reasonably accurate. And you basically design on the principle that the outside surface of the timber will burn, but it then sort of creates a preventative layer around the rest of the timber. And so you would just ensure that you were going to have enough timber left in the middle to still transfer the loads down to the ground. And I think this diagram kind of shows it quite well. If the timber didn't have anything on the top of it, you would also calculate the charring around the top. In this situation, it's got a floor on top of it, so you would be looking at the charring around three sides of the timber. And when we come to look at engineered timber products such as CLT, you would look at them in the same way, but there are some other issues that you have to take into account. So you would kind of expect that in CLT, the first layer of the timber would probably char most of the way through, but then theoretically that should protect the rest of the CLT. The issue with this has been that lots of CLT is manufactured with glue that doesn't have any fire resistance or heat resistance. So actually what happens is the outside layer burns through, the glue melts, that layer comes off, and then the next layer starts burning, and actually you get a completely different fire response because instead of having this kind of steady curve where the outside burns quite quickly and then sort of plateaus off because there's nothing left on the outside to burn. That layer falls away, and then you get this accelerated fire response on the next layer. So one of the really important things with engineered timber products is to specify that the glue that's used in them is heat resistant, and so that doesn't happen. And on the Old Street project that we just were looking at, that was one of the things that we had to do in our specification. And I think they did a lot of testing to prove that the glues that they were using were not going to have a response to heat. This is also something that has only just started to be included in codes that structurally we use to design to. So it's something that's kind of changing all the time. There are more changes to the codes later in the year, I think. And so it's something that will continue to change in the way that we have to design for it. That is obviously kind of using the outside layer of the CLT as a sacrificial layer. You can also put another layer of timber on the outside that is the sacrificial layer that you're designing to burn, which has been done successfully in lots of places. This I've included, this is Elephant Park Pavilion, which we have been working on, and you may have seen it in the news last summer when there was a fire there, which sort of sounds very dramatic, that it's this CLT structure which had a fire. Actually, I think it was some insulation which was stacked on top of it, which caught on fire. And in the end, the damage to the CLT from that was incredibly limited, and the damage to the handrail around it, which is steel, was much greater, and the handrail had to be replaced, but I believe the CLT didn't. So it's quite interesting that it has this sort of stigma that it's timber and so it will definitely burn, and actually in this situation it wasn't the CLT that there was an issue with, it was the steel around it. So the first two projects that I've talked about are commercial office buildings, and the much bigger issue is when you come to be trying to use timber in residential buildings, and that most of the requirements from the Hackett report refer to residential buildings. In reality, those sort of stipulations about limiting the combustible materials in the facade and the use of timber as a risk-averse approach often get sort of applied on commercial buildings as well. But obviously when you're building a residential building, they are much more important. So this project is Peckham Rye, which was designed by Takari Works. And here we did a CLT superstructure, which is on top of a sort of concrete plinth, and these houses also have basements. And you can see internally this is all CLT, which actually in reality there is very little risk from it, but there is this stigma again attached to timber and timber in residential buildings. And I think that some mortgage lenders in particular are slightly awkward about this. For residential properties, timber counts as an unusual or special building material, even though it's obviously incredibly common. And so sometimes there are some mortgage lenders who don't really like it, and so I think possibly on this project the developer had to help some of the buyers to find mortgage lenders who were happy to consider it as an option. Again, on this project, the embodied carbon is significantly reduced by using CLT. So it has massive benefits. It's a really warm space for the residents. It's just overcoming the sort of stigmas attached to that. And the last thing that I was going to mention is that it's much more likely that sprinklers are going to be required on the project, and I believe it's kind of like misting sprinklers that are usually needed. This isn't a project with sprinklers. As I said earlier, lots of these things we don't have projects where they are included yet, so I've just given you a picture of one of our other timber projects. But we found that it's really important to have the conversations about fire early on, because things like sprinklers are often required on projects where you wouldn't necessarily expect them to be required. So just to kind of summarize the key considerations that we found. Firstly, choosing a fire engineer and building control who have experience with timber and are familiar with working with timber buildings. And it's really important to be starting to have those conversations really early on in the design process. It's likely that in a taller building, full-scale testing or more advanced modelling for fire is likely to be required. And it's unlikely that both the walls and the ceiling in a CLT structure are going to be able to be exposed. When you're looking at any exposed timber, the charring depth needs to be considered. And in CLT, the charring depth needs to be considered with the possible impact of delamination. And finally, that sprinklers might be required even in low-rise buildings.
Wow, all those live fire tests, fascinating but demanding. And thank you very much for the summary at the end, which I think is real food for thought. We are getting a lot of questions coming in, but do keep sending them. I'm really looking forward to our discussion at the end. But before we get to that point, I'm delighted to introduce Dr. Jim Glockling, who is our final speaker, and he is Technical Director of the Fire Protection Association. Jim.
Thank you very much for the opportunity to talk today. My short talk will be based very much around the white paper released in February, produced by RISCAuthority on the insurance challenges of massive timber construction. Funded by the UK insurance industry, the membership of RISCAuthority makes up a significant component of commercial insurers in the UK and overseas. The two key takeaways that I'd like to really leave you with, but worth stating up front, are first and foremost, designers will need to build in features that enable the insurer to assign an estimated maximum loss, or EML value, that is something other than 100%. Now, this doesn't happen natively when compliance is the only design goal. I'll go into detail later of what EML actually means. But also, another key feature is that this conversation is not just about wood, and it's not just about fire. And in fact, some insurers consider escape of water and flood a greater threat. Now, the insurance perils that we're considering as part of this undertaking include fire, escape of water, and flood, and these contribute to different insured loss types, including material damage, business interruption, loss of stock, loss of rent, and displacement costs. Now, a little bit more on estimated maximum loss. It would be very expensive if we had to insure every building as though it was going to be a total loss in the event of every fire that started. And so to look at this, what might be assumed for any given building is that you might not lose the whole building, but you would lose a portion of it. And in this particular example, for this building, we might lose the fire floor, as you can see there. We might lose 2 floors above, or have damage incurred in 2 floors above by smoke damage. And perhaps through the firefighting activities, we might have damage incurred on the floor below to water damage. It's a very simplistic model, but I think what you can see there is the estimated maximum loss in the case of this 17-story building is only 4 floors. But we've got to consider about other design features that may be introduced that stop this model from working. And I hope you can see that this is a hard-earned a feature for any building to have. It implies high levels of compartmentation, no external fire spread, and that the structure of the building remains sound throughout the fire. But we've got a lot of challenges coming up, not least green walls, as you can see there, which have the potential to promote external fire spread. The bottom left picture shows modular construction, and in its combustible form can lead to the inclusion of many combustible voids within the building that may contribute to an increased potential for internal fire spread. And obviously you must also consider the construction period as well, bottom right, where in the case of timber, many timber methods, the fire resisting skinning of the building is the very last thing that happens. So it has a considerable period of being very vulnerable to fire. I mentioned that it's not just about the features of whether it's a combustible building or not. And actually, when we have a look at this and analyze any building, we have sort of 6 key categories that we will consider when looking at risk. We'll consider how it's used and occupied. The scale of the building is obviously very important. The structure and the fabric of the building and how combinations of materials are used. But there are other risk factors too, such as the inclusion of atria, balconies, basement car parks, green surfaces, green energy, etc. And they all can be offset somewhat by the inclusion of measures to mitigate fire, such as protecting voids, inclusion of suppression systems, and also measures to mitigate the challenges of water as well. So specifically in building features design to protect against flood and escape of water issues also. Now, the other thing to consider is the relevant types and periods of insurance that can be impacted. We're very used to construction. I don't think I need to say too much about that because we've had a lot of experience with light timber frame on that. On the third one, material damage and business interruption, I think is very simple to understand also. What might be less known is the potential impact that moving to a more wooden-based large building method can have mean for latent defects. Now, latent defects insurance is normally associated with fixing for a period of times small-scale defects such as leaking windows and leaking roofs for a period of 12 or 15 years into the building's life. Certainly there's no element in there that would be protecting against anything that might cause a building to collapse. But now there is consideration being given to some of the massive timber techniques and the response of some of the, or potential response of some of the materials to water damage, that there may be potential for severe structural implications of the building under latent defects cover. And that takes us into a very different realm of insurance. Now, many things actually impact the overall cost of insurance. I won't go through these in detail, but when we deal with a new building method, certainly repairability considerations, availability of new materials, whether anyone can actually assess the extent of damage, all become important features that can modify the cost or indeed the insurer's confidence at understanding what they're taking on. Now, through RISCAuthority, we produce a wide range of documents, but in these are a suite of essential principles, which is a good starting point for anyone wishing to understand the insurer mindset for risk, and particularly when it comes to building susceptibility to overall resilience, fire, flood, and escape of water issues. Now, obviously, others will be talking about this in great detail, I'm sure, but they're huge and very meaningful drivers to a net zero future. It does seem to be being done with quite a single-minded form, and there is concern that maybe consideration isn't being given to some of the potential impacts. Now, hopefully it can be achieved without reducing safety, but certainly we've already seen implications with other building methods that do have ramifications for property resilience, business resilience of the work that goes on inside them, the service delivery of any business conducting from the buildings, and also we also need to consider how whether the buildings adequately support the fire and rescue services so that they can be effective in this environment as well. And when you group all these things together, there is a big question about whether the move can be done while maintaining the insurability of the building itself. So we've moved from a position where we're used to of concrete and steel, and we know that as materials, they're pretty good in being resisting fire and also water issues. And we're moving to a very new domain of panelized and post and beam and modular construction, often in association with other green measures such as green energy systems and green walling systems as well. So a very different environment to be moving into. I won't dwell on the types of timber construction, but it's worth highlighting. We're talking really very much here about heavy timber framing. We have great experience now of light timber framing, and I must say that it has presented a challenge for insurers in their own right. Some of those lessons learnt there may cause concern moving forward to other timber-based building methods also. But principally, the types that we have, glue laminated veneer lumber, generally used in post and beam type constructions, and panelized systems like cross-laminated timber. So these are all the things that have changed, but it's really important to consider what's not actually changed. And crucial to this is our building regulations. They have been changing, but they've been changing in a rather adverse direction over the years. All of the other factors that contribute to a building's insurability that we've mentioned previously. Importantly, how people expect buildings to perform in fire, and the expectation of availability and cost of insurance and lending. And this can lead us down to some difficult conversations, which hopefully this talk is starting to go some way towards addressing. Now, I've mentioned building regulations. In the UK, our building regulations have total divorce of property protection and life safety. So as such, their only focus is really evacuation before collapse. That is to say, in the time that it takes for the fire to take hold of a building and cause it to collapse, it should have been successfully evacuated. And they do this very well, but it is at the expense of the, or it can be at the expense of the level of destruction of the building. Now, in other countries, they take a different approach where actually life safety follows really the passive capability of the building to perform under fire. And certainly in the US, we see language which we certainly don't see in the UK building regulations about preventing collapse, preservation of current cultural heritage, mission continuity. This is really at the core of business continuity planning and ensuring that there's something left to save at the end of the day. Now, this has led us down a difficult path in the UK, and we see that the provision of insurance and the capacity of money provided for insurance in the massive timber sector is very problematic. And by definition, it's almost as though the insurer and the lenders are becoming the de facto regulator currently, and that is not a good position for anyone to be in. So we really do need our regulations to respond to this, or indeed for the designers to start addressing insurers' concern adequately. If unaddressed, though, we do need to ask ourselves as to whether this really sort of presents the new norm for us. Now, in these buildings, nobody died in them, and they may well have been compliant, but are we really looking at a future where fires end up with buildings on the floor? Now, insurers are concerned with large-scale fire spread. Three principal mechanisms. We're used to external fire spread, and hopefully post-Grenfell, anything like this reoccurring is a thing of the past. Internal fire spread is very well catered for within our building regulations, and compartmentation is fundamental to the preservation of life. And that's the language of fire doors, dampers, and everything else. But what these new building methods, combustible building methods can introduce is really a third mechanism for fire spread in the shape of combustible voids. And just as a fisherman's net can be described as a lot of holes sewn together, if you actually look at some of these walling structures, the highlighted areas there, these are all voids. So actually a wall is now, rather than being a contiguous non-combustible item, really is now a collection of voids, and that presents opportunities for fires to spread around unnoticed, out of reach of fire service, and out of reach of any suppression system. And if that is also the structure of the building, it will result in loss of the building. So that's on a macro scale, but on a micro scale, there are other changes needed too. Certainly panelized systems can be quite prevalent in the sort of hotel and apartment and residential arena. And this can be problematic if we just look at one key area of bathrooms. Bathrooms are generally stacked one on top of the other. So if fire can spread out of one, then it can affect all. It's a location where key services such as risers can communicate fire to at all levels. There's lots of plastic in the form of the bathroom furniture and sinks and what have you. They have false ceilings, again, more voids, loft hatches, which can be a weakness. And there's no requirement for suppression because they're generally or historically been considered quite inert. But when we look at them now, actually, you can certainly see in this sort of environment a need for reinforcement of the fire stopping, because actually to consider fire actually getting into any of these voids might be almost inconceivable because they may then be beyond saving. So if we look at this in the context of a fire gets into a combustible void, we know that smouldering combustion can relish the low oxygen environment, eat away for many hours or even days before emerging. And it becomes very difficult to answer the question of what will ultimately put the fire out. It's not in the realms of any suppression system or the fire service, and we need something to respond to that. But if the whole protection concept of a building of this type relies on ensuring fire cannot get into a void, because if it does, the building is lost, that's a very difficult thing to consider. Now, obviously, if UK insurers had their way, we'd have buildings which are made of materials which can't possibly burn, very well compartmented, but they're not going to be pretty. And they'd probably all end up looking like this. And these are not the sort of buildings which we need or want. So there must be a better way forward. We mentioned previously that building regulations must respond. And certainly when we look to the US and things like the International Building Code, they have responded. The whole concept of a combustible void doesn't exist because if you have a combustible void, by their building regulations, the materials inside it will be controlled, and they will either be protected by a sprinkler system, or they'll be lined out in non-combustible materials, or indeed the void will be filled with non-combustible fibrous material insulations. So there are ways of dealing with this. We're just being very slow. So the future, probably for acceptable buildings, might be looking at hybrid solutions. And there's the where we select the materials in accordance with the risks as they arise. So we know that placing buildings on a concrete plinth can protect against flood and many escape of water challenges. If you build out a concrete core, you may get better support from the fire service with the assured structural stability of the building under fire. It's also a location where all services could be routed in non-combustible ducts. It's a place where kitchens and bathrooms and escape of water hazards can be located. So I'm sure that the future will be one of hybridization, and that certainly seems to be the path that many designers are taking. And there are some very nice designs coming out which have sort of addressed many of the features of the white paper that have been produced. So it's certainly very encouraging to see. And let's not always think of the concrete elements as being evil in hybridization, just as wood can be net zero. I'm sure there are low carbon versions of concrete to give the overall environmental credentials that we're actually looking for. So in summary, it's a time of great change. We know that probably wood is the future, but actually it's probably a hybridization of materials that's the future to produce something which is insurable and livable in. I do believe that desire to build is running ahead of some of the research for some of the materials that we've got. There needs to be modification of building UK regulations to change this. And whilst skyscrapers seem too difficult to consider currently, we have seen designs at different scale and with forms of hybridization that certainly look very reasonable to me, and hopefully will in the future to insurers also. But I think the key takeaway, designers must understand the importance of EML and what they can bring to the table to reduce it from the off. Thank you very much for the opportunity to talk to you today. I know it's been rushed, but if you want more information, the white paper is downloadable from the RISCAuthority website. Thank you.
I'm not sure I'm ever going to feel the same about being in a hotel bathroom again. Again, lots to think about, some of it a bit worrying and obviously with big implications. And lots to discuss. So I'm going to bring our panel back in now and address some of the questions that have been sent in. And there have been several questions coming in about charring, particularly about what happens after the charring, after that event. Is the structure regainable, or is that something that just has to be thrown away? I would like to ask Anna first how you look at charring.
I think it would depend on the building and the way that has been designed. If you had done something where you had a kind of sacrificial layer of timber on the outside that you were able to remove, then it might be possible that you could do some repairs, and also depending on how badly affected the building had been by fire. But I think that there would, if you had a bad fire and it had sort of charred all around the elements in the way that we were describing, I would expect that you would have to replace some of those elements. That's not that different to the way that you would design other types of structure. For example, when we consider other things in other sort of things that we design for, so when we design for example, disproportionate collapse, if you had some other damage in a building, if a vehicle drove into a steel column or something, you'd be expecting to replace that, and you would design the building to not collapse in that situation and be able to deal with that, but you would still have to replace an element. So I would expect that you would deal with it in a similar way. I mean, we are not fire engineers, so a fire engineer might have a slightly different answer to that, but my expectation would be that yes, you would have to repair or replace some of those elements.
Steve, you're not a fire engineer either, but we have had questions come in about the charring on your building, and in particular, and this is, I have to say, not something that I know about, but somebody said that different timbers char in very different ways, and they're interested to know what you are using, what the actual timber is that you're using on your building.
It's right, all timbers act differently in a fire, and it's a European spruce that's used in the work stack. And there's been a lot of, speaking of fire engineers, there's been a lot of detailed coordination with our fire engineers and the timber suppliers to understand exactly how the timber will function in a fire, and making sure that there's the design of the building meets those requirements. And so we've made sure that a fire would break out only in one area of the building and not be able to spread to multiple areas. So all panels are designed so that if there were a fire, it would only affect one side, for example.
I'm going to ask you something else first, because again, it's something that people have asked on that particular building that we saw, that the architectural impetus for the cantilever, I think, is very clear and is lovely. But there was concern about fire coming up under the cantilever, and how you'd actually looked at that.
And so Arup are the fire engineers on the project, as well as the structural engineers. And so in a similar way, the idea is that a fire is kept within the compartments, but in that western facade, there isn't a possibility that it could come up into outside the building. But we're fortunate that that whole side is where the fire brigade would have direct access, and so any fire could be easily dealt with on that side, as opposed to the other sides are more constrained.
And Jim, I know you wanted to ask about this, and I just, before you make your answer, I would say that people have come in with questions saying, because the EML in timber buildings is higher than in concrete buildings, will they calculate the premium based on total losses? You might answer that,
yes.
but also you've obviously got things to say about charring.
Yes, well, first of all, on the subject of EML, certainly where there is a lack of knowledge or where there is evidence that damage will be higher, then it will be given a higher EML. And that can affect many things, such as premium setting. I lived in a thatched house for 17 years. If I had a fire in the roof, it only ends one way with a total loss. And as a result, I was paying every month what I think most people pay in a year for building insurance. But I think you can appreciate it. It can only be that way for that particular scenario. So I think the crucial thing is to build in measures. We've got to get to a place where buildings are insurable, but there's no free lunch. And charring is very much sort of relevant to this. It's important to bear in mind that charring isn't the end of the fire event. It normally represents a transition from flaming combustion to a sort of smouldering combustion. So it's a slowing of the event. But smouldering combustion is very dogged and determined. And I've had to babysit through the night, many test rigs in massive timber where the smouldering will persist and it will break out the other side of a wall perhaps 9 hours later. But it does it, and that's why it raises this question of what actually ends the fire event at the end of the day, and that's it is one of the most difficult questions to answer, especially if voids are involved. Someone mentioned about sort of designing self-extinguishment by design as a protection method, and I've even heard people say that this can be done with such rigor that you don't need sprinklers. Now, I can't really buy into that just because there's so many controls need to be in place to ensure that can happen robustly. And remember, fires happen at a time of chaos, and things generally they start because things that should be working shouldn't. So we need to find more sort of robust means to actually control fire and control the consequential damage caused by any systems that might actually be deployed in the process also.
I've also had questions coming in about chemical treatments and misting sprinklers. Somebody asking really how much insurers are willing to rely on those. And another question saying, do you agree that the vulnerability and risk of the use of timber is much diminished in the modern day due to the evolution and science of FR treated products?
Well, certainly there's a large role to be played by FR treated products, and certainly the work done with the STA as an enabler for construction site progress has certainly warranted great benefit. In respect of sprinkler systems and misting systems, we need to be very clear on the design purpose. And again, it's whether they are in there to protect property or to protect life. And some systems are better at doing one than another. Generally, if you want to protect property, they're very high resilience systems. And we're generally looking at sort of commercial type sprinkler systems, which have very high integrity water supplies and are designed to ensure the end of the event, and of course their contribution that they make to overall safety. So many insurers will recognize those with a water mist system, which can use very limited quantities of water, very effective preventing flashover for the period of time of operation. They are generally employed for life safety purposes to ensure that the occupants have enough time to escape from a difficult situation. So the insurers all have their own views on this as to what they're prepared to recognize. But generally, they're the more commercial type systems to protect property would be the recognized systems of preference for them.
And I think that brings us to David, who's certainly someone who has been looking at fire-resistant products and impregnation. One of the questions is how your products work together with other products. So does it require a fire-treated timber frame as well if you want to do that vital improvement to the spacing? Or does it work with a standard untreated frame? Because I think we all know that it's never one individual product that matters. It's the whole system and the whole building, isn't it?
Absolutely, Ruth. Yeah, and I did mention in the presentation that the whole industry kind of got together behind this issue, I suppose, and there was really great collaboration between manufacturers, specifiers, and all key stakeholders in this. So you're right. It's not just the performance of one product. So the small room test that I showed there is not just the performance of our product. For example, where the crib is, directly behind the crib, there's a non-combustible, I think it's type 2 flame retardant insulation. The studs are FR treated then as well. So it's a system build. And obviously, as I mentioned in the tables, there are different levels of separating distance. So, category A is untreated timber frame, and then category B gives you various levels. I think that B1, 2, and 3 gives you various levels of performance and hence separation distance. And then you're into category C, which uses non-combustible panels and boards. So depending on the height of the building, the size of the building, and the proximity to neighboring buildings will all depend on what products are used in that system. So the in the design process, which is quite technical and complex, the timber frame designers particularly need to go through all of the products and the data that they have available to them and choose the best one. So yeah, in summary, it's a system, and you need to be very careful. Don't just assume that it's a product works with something else. It has to be in that test. And in the output of the STA guidance, there are product papers. I think it's product paper 4, and you can see the system builds. Ours is 1. There are other manufacturers with systems in there as well. And then the products themselves may or may not have FR build status on their own right, for which we have for 15 millimeters thickness and above.
We've also had questions about toxicity and environmental impact. I'm going to ask you again, David. People are obviously concerned when you add anything to a material that they know and love. And people are saying, is there toxicity in event of a fire? Is there a negative environmental impact to using these products? And I guess how sustainable are they? And I guess that part of that is to do with if, and we hope in most cases it's true, they won't have encountered a fire at all. How much can you reuse, recycle at the end of life of either the product or the building?
Wow, how long have I got?
Oh, well, about 30 seconds, I think.
Wow.
Give us the short answer.
I think the first part is, in terms of toxicity, we've been adding flame retardant additives. I like to use the word additives instead of chemicals. Chemicals sounds a bit nasty. So we've been doing this since the mid-1980s in MEDITE, MEDITE flame retardant MDF, and that product has been through so many fire tests over the decades, including toxicity tests, smoke density, and so on. So it has passed I suppose the scrutiny of lots of different stakeholders and tests and so on. So the second part of that is smoke is obviously the killer in a fire. If you have a Euroclass B, you have to designate the smoke class as well. So our MEDITE products would be in the smoke class S2 or S1, S1 being the highest. Toxicity, back to toxicity as well, we use in the OSB product that's shown there, that is a water-based additive that we use in there, which has been screened for lots of different toxicity measures, so damage to plant life, aquatic life, and so on, and obviously when it burns, and as well what gases it gives off. If I can just give I suppose an example of that, when we started developing these products, we looked at 3 different routes to doing this, and one included coatings and intermittent coatings, and we just weren't satisfied that they would work because of the gases that they gave off. So there are issues with certain coatings in that regard. In terms of environmental performance, so I kind of figured this would come up because obviously we're talking about sustainability here. So I mentioned on a previous webinar, if you look at the carbon footprint of this particular product, the SmartPly Max flame retardant, so the footprint of manufacturing the products, so the extraction of materials and production, emits 386 kilograms of CO2 equivalent per ton of the material. However, the biogenic carbon content of that product from the tree and the wood that's used is negative, so it's minus 1,540 kilograms of CO2 equivalent. So the total carbon footprint of that product is obviously negative to the tune of 1,150 kilograms of CO2 equivalent per ton. So extremely safe and sustainable product to use.
Wow, thank you very much. That really was a lot of figures at your fingertips, wasn't it? A question for Anna. You were talking about particularly sort of heat build up in the joints in CLT. And somebody asked whether there are steel connections in there and whether those in themselves need fire protection.
I'm not completely sure on the Old Street project that I showed exactly what those connections are. On the photos, I think it looks like it has some strapping, which might be doing something. It would completely depend how you had designed that joint and what was exposed and what wasn't. But potentially, I would guess you might need to do some protection if they're still in there. I think there are a lot of other things that are that come into play when you start looking at those joints as well. And I think that there is a lot that's to do with. So I think even when you look at putting plasterboard to cover timber, there are issues to do with that is not just the sort of like that insulates the timber, but it does prevent the heat buildup. And I think that's part of the issue when you're looking at those joints, that it's to do with the heat buildup and the like ignition temperature, and how close you're getting to that. But yeah, I think it would depend how you were using any steel connectors in there. If you were fixing it together with maybe a steel angle or something, then and that was a critical part of that structure, then I would expect that you would have to be providing some fire protection to that, whether that was covering it or some intumescent paint or something. But well, I'm not. I think it's quite involved and how you would look at that. Now I'm like thinking through like, actually, would that work because of how an intumescent paint actually works in reality? But I think it would depend exactly how you were using it, and it would probably be different in every situation.
I think one thing that came through in your presentation, which rather shocked me, and I think it's my fault because I hadn't thought about it, was talking about CLT delaminating with glues that weren't designed to resist heat. And I suppose it just made me think, my goodness, why wasn't everyone doing that already? And I think I'm just going to take that as a jumping off point to ask each of you what you think is going to change and have to change in the future. What from your, I'll ask you first because we've been talking, Anna. What do you think is the big difference that's going to happen going forward in your design of timber buildings?
I think first of all that we should still be trying to use these products, and I think sometimes it's very easy to see the fire as a big issue and for it to sort of blanket be ruled out because there are so many issues with it. So I think like for us, I would say we really want to keep trying to find solutions to all of these problems and overcoming the issues. What do I think are going to be the biggest changes? I think, I mean, I definitely think that the having sort of multiple, what am I trying to say? Multiple sides exposed in CLT and internal spaces is going to be something that we're not going to be able to do, and that things will need to change in order for us to start doing that.
Yeah, no, I think that's really interesting, and I want to know whether Steve is thinking the same way, that you're going to no longer have multiple sides of CLT exposed.
I think that's one part. I suppose I was thinking coming at it from the climate emergency that we're currently living in and addressing. Timber presents a really good opportunity to build using the least embodied carbon in our structures. But it does feel like in order to realize that potential, there's a lot more testing and standardization of timber products that's necessary. And I think through that will come regulation change. And so I suppose that's the challenge, I suppose, to the industry is moving with the times and appeasing the regulators so that we can hopefully see a bit more timber buildings that address the concerns that Anna's raised, and probably a lot more that we're not aware of yet.
And Jim, you said something which was a little bit chilling, which was that you thought that our design and enthusiasm was running ahead of our research. Doubtless you'd advocate more research. Do you think it can get us to a stage where we can continue to use a lot of timber in our buildings for all those very good and valid reasons, and without the insurers being too scared?
So I think the encouraging thing is that the change is happening. And I think the future is going to be one of hybridization of materials, so they're used in the most appropriate place possible. So the overall sum of the building is meeting the sustainability expectations needed going forward. I think there also needs to be a recognition that, as I said before, this isn't just about fire. Many insurers consider escapable water to be a greater peril because they are such prevalent events. Fires are very rare. Escapable water events very prevalent, and the designs which are coming to the fore and the research that is being done by the likes of Arups and those with the new modern model, and other groups working on this, I think it's all encouragingly heading in the right direction. And the most advantageous thing that's happening is really maybe with the bigger providers are having very early conversations because of their very good relationships with their insurer. They're having those conversations early, and progress is made from the start. So I'd say it's all very encouraging.
Encouragement is what we want. I'll just come back quickly to David, because you're both responding to and doubtless trying to be ahead of what the industry wants. And are you seeing that there is more appreciation of, the point of rigorous fire testing, etc.? Are you seeing changes?
Yes, absolutely, Ruth. I've seen it from both sides because I've come from a technical background. I'm a wood scientist, so I'm all about wood, but I'm all about wood in the appropriate use of materials and wood in the right places. So it is not the answer to all of these problems. That's the first thing I'll say. I've come from a technical and innovation background within the company. So there I was all about looking at the challenges, looking at market drivers, technical challenges and issues and so on. How can we solve problems? So yes, we like to stay ahead of the game. It's not always possible for a manufacturer to be first to market. And this is one example of this where this happened. We were not the first to market with a product because of the complexity and testing and certification that goes behind it. It does take time to get it right. So as manufacturers, we have to stand over all of that. And I think that's where I see this, the demand coming through is now, it's a chicken and egg. A manufacturer will get behind a market movement, and I think this is a market movement. So when you have a compelling commercial case to develop new products and systems, obviously manufacturers get behind it. It's where massive investment in the millions is invested in this kind of technology. You obviously have to have a business case that underpins that level of investment, and that's what the manufacturers need. So it comes about from this kind of thing is fantastic. This is where conversations happen. And from this, collaborations are formed, with the universities and the technical institutions and the manufacturers and specifiers all getting together and understanding the issues. And then you can really see the shift and the change in an acceptance of timber buildings. And constantly we're getting asked for solutions. Does your board do this, that, or the other? In some cases, gladly, we're able to say, yes, it does, because we have the certification behind it. But in other cases, we have to say, no, we don't know. If there's enough people that want to know this, of course, we get involved in testing. But at that point, you start a new train of research and development, and that's where it goes from there.
Well, you mentioned that this is where the conversations are happening, and I'm delighted to say that there are going to be more of these conversations. This is just the first in a series of 4 timber and construction webinars that Architecture Today is running with MEDITE. The next one will be on the 15th of June. So everybody, please put that in your diary. And I think I'm afraid we have run out of time, despite the fact there's so much more to say. So really all it remains for me to do is to thank all our speakers, to thank everybody who's been watching, particularly those who sent in questions, and to say goodbye and see you again soon.